Welcome. Today, we're diving into the world of decision tree learning, a fundamental technique in machine learning for approximating discrete valued target functions. Imagine a tree-like model that helps you make decisions by sorting data from the root to a leaf node, where each leaf gives you a classification result. This method is widely used because it's intuitive and effective for many types of problems. Throughout this video, we'll explore how decision trees work, their strengths, and the key algorithms behind them, setting the stage for a deeper understanding of machine learning models. Decision trees classify instances by guiding them down the tree, starting at the root and moving through nodes based on attribute tests. Each node represents a question about an attribute, and each branch corresponds to a possible answer. As you follow the branches, you eventually reach a leaf node that provides the final classification. This structure makes decision trees easy to interpret and visualize, which is why they're so popular in both academic and real-world applications. Let's look at how a typical decision tree is structured and how it sorts data step by step. Each path from the root to a leaf in a decision tree represents a conjunction of attribute tests, and the tree as a whole represents a disjunction of these conjunctions. For example, a path might test if the outlook is sunny and humidity is normal, or if the outlook is overcast. The tree can be translated into logical expressions, making it a powerful tool for representing complex decision boundaries in a simple, visual way. This logical structure is what enables decision trees to handle a wide variety of classification tasks efficiently. Decision tree learning is best suited for problems where instances are described by attribute value pairs, and the target function has discrete output values. They work well when you need disjunctive descriptions, can handle errors in training data, and even cope with missing attribute values. This robustness makes decision trees a go-to choice for many practical machine learning tasks, from medical diagnosis to customer segmentation. Understanding when to apply decision trees is crucial for building effective models. At the heart of decision tree learning is the ID3 algorithm. ID3 constructs trees top-down by selecting the attribute that best classifies the training examples at each step. It starts with a root node and recursively splits the data based on the attribute with the highest information gain. This greedy approach continues until the tree perfectly classifies the training examples or all attributes have been used. ID3's simplicity and effectiveness have made it a foundational algorithm in machine learning. Key step in ID3 is selecting which attribute to test at each node. This is done using a statistical property called information gain, which measures how well an attribute separates the training examples according to their target classification. The attribute with the highest information gain is chosen, ensuring that each split brings the tree closer to accurately classifying the data. This process is repeated at every node, making the tree both efficient and effective. Entropy is a measure of impurity or disorder in a set of examples. In decision tree learning, entropy helps quantify how mixed a collection of positive and negative examples is. If all examples belong to the same class, entropy is 0. If the classes are evenly split, entropy is 1. Most real-world datasets fall somewhere in between. By calculating entropy, we can determine how informative a particular attribute is for splitting the data. Information gain measures the expected reduction in entropy after splitting the data based on a particular attribute. For example, if splitting on wind reduces the uncertainty in the dataset, that attribute has high information gain. The ID3 algorithm uses this measure to decide which attribute to split on at each step. By always choosing the attribute with the highest information gain, the tree becomes more accurate and efficient. See ID3 in action with the classic play tennis dataset. Here, each day is described by attributes like outlook, temperature, humidity, and wind, and the goal is to predict whether tennis will be played. ID3 calculates the information gain for each attribute and selects the one with the highest value outlook, in this case, as the root node. The tree then branches out based on the possible values of outlook, continuing the process for each subset of data. After selecting the root attribute, ID3 continues by splitting the data into subsets for each value of that attribute. For example, all days with rain are grouped together, and the algorithm calculates information gain for the remaining attributes within the subset. This recursive process continues until each branch leads to a leaf node with a clear classification. The result is a tree that can accurately predict outcomes for new, unseen data. ID3 searches through the space of all possible decision trees, starting from the simplest and moving towards more complex structures. It uses a hill-climbing strategy, guided by information gain, to find a tree that fits the training data. This approach ensures that the hypothesis space is complete, meaning every possible function can be represented by some decision tree. However, ID3 only maintains a single hypothesis at a time, which has both advantages and limitations. Inductive bias refers to the assumptions a learning algorithm makes to generalize beyond the training data. ID3's bias is a preference for shorter trees and for placing attributes with high information gain near the root. This preference, known as preference bias, is generally more desirable than restriction bias, as it allows the algorithm to explore a complete hypothesis space without excluding the true target function. Occam's razor is the principle that the simplest solution is often the best. In decision tree learning, this means preferring shorter trees that make fewer assumptions. Shorter trees are less likely to overfit the data and more likely to generalize well to new examples. However, it's important to balance simplicity with accuracy, as overly simple models may miss important patterns in the data. Overfitting occurs when a decision tree becomes too complex and starts to fit the noise in the training data rather than the underlying pattern. This can lead to poor performance on new data. To avoid overfitting, techniques like pre-pruning and post-pruning are used. Pre-pruning stops the tree from growing too deep, while post-pruning removes branches that don't improve accuracy on a validation set. The goal is to find the right balance between fitting the training data and generalizing to unseen examples. Reduced error pruning and rule post-pruning are two common methods to improve decision tree accuracy. Reduced error pruning removes subtrees if doing so doesn't decrease accuracy on a validation set. Rule post-pruning converts the tree into a set of rules, then prunes each rule to improve accuracy. These techniques help create simpler, more robust models that perform better on new data, making them essential tools for any machine learning practitioner. Decision trees can handle continuous valued attributes by partitioning them into intervals or using thresholds for splitting nodes. For example, temperature can be split into ranges like high, medium, and low, or by using a threshold such as temperature 54. Additionally, alternative measures like gain ratio can be used instead of information gain to prevent attributes with many values from dominating the splits. These enhancements make decision trees versatile for a wide range of data types. Real-world data often contains missing values or attributes with different costs. Decision trees can handle missing values by assigning the most common value or using probabilities. When attributes have different costs, such as in medical diagnosis, the tree can be adjusted to prefer low-cost attributes, only using expensive ones when necessary. This flexibility makes decision trees practical for complex, real-world problems.